must be a classical version of all this fault tolerance.
Sort of.
So at some point I went to look a little bit many years ago, and I couldn't find anything that was.
Well, so there's a very, very simple classical fault-tolerant protocol, which is the code you use is the repetition code, and then you just do everything, all the same circuit over and over again on the repetition, and then occasionally you have to do error correction by comparing. The problem of getting a real analog of what we're doing here classically will show up today when we start to talk about getting a universal set of gates. And we're going to do that by sneaking in classical computation. As you know, but probably the rest of the class doesn't yet. Yeah?
Classically, we don't assume any faults in the error correction circuit, so...
well, so I mean, right. So you can do all that calculation with I mean, so yeah. So the repetition code is just so simple and straightforward that you can work out circuits that will handle faults in them and still do error correction robustly. That's the only thing that's at all tricky about the classical fault tolerance is making sure you do that right. And you're helped there by this fact that classically you can have controlled gates where things can only propagate forward and not backwards. Right? So if you have a controlled NOT gate, classically the bit flip can propagate forward, but there's no phase flip to propagate backwards. So you don't have to worry about what happens to the control if there's an error at the target. Yeah, I mean, actually, you're doing it with Toffoli gates, 3-qubit gates. Yeah.
Is there any quantum gate that propagate error only one way?
No.
No.
No. Yeah, I mean, it just can't happen. The most interesting exception that I know of is the swap gate, where so you take the 2 qubits and you swap them. So it does, of course, propagate errors from here to here and errors from here to here. But the thing is, the errors don't stay where they started, right? So if you had pre-existing error here, you do the swap gate, you now have one here, but not one here, right? So then you know kind of that it didn't go to more qubits, right? It's the same number of qubits, they're just different qubits. But of course, it's a 2-qubit gate. So if the gate itself has a fault, you could get errors in both qubits. OK? Any other questions? OK. So yeah, so getting back to this point. So we want to get a complete universal set of gates. So far, what I've talked about is fault-tolerant gadgets. Well, for error correction, for state preparation and measurement. And we did transversal gates as the very first thing. But as you saw for the 7-qubit code, that was just the Clifford group that we could do transversally. And that's actually a lot. Most codes, you can't do even that much. So there's actually a very general result, even for non-stabilizer codes, that said there's no universal set of transversal gates. That's the Easton-Nil theorem. I think Benny will be covering it at some point. I'm pretty sure it's in the book. Yeah, pretty sure it's in the book, but not 100% sure. Anyway, so in order to get a universal set of gates, in fact, the Clifford group is not just non-universal, but it's classically simulatable. So if we want to do some exponential speed up using a fault-tolerant quantum computer, we're going to need some other kind of gate construction that's going to be more complicated than the transversal gates. And so this type of gate construction is called magic state injection. And so the basic idea to understand how this is going to work, we're going to think about teleportation. So what is teleportation? Well, you have an EPR pair. So right now, just let's think about unencoded. Okay, forget about error correcting codes for the moment. And I just want to try to find a way of breaking down gates in a different way than you'd normally think about. So we have some state. We have this. This EPR pair, and we do some Bell measurement, getting 2 classical output bits. And then, depending on these 2 classical bits, we do some poly here, and the output is the state psi. Right? Now, obviously, teleportation, the way we normally think about it, is useful in the context of communication, where instead of sending a qubit from Alice up here to Bob down here, you just have to have a pre-existing entangled state, which you could have developed through a lot of work. And then you only have to send classical bits between them at the time you actually want to send the qubit. But what we're going to be interested in is computation. And so we're going to think of all of these qubits as being just right next to each other in a quantum computer. And so what I want to start out by doing is something that will probably seem very stupid, which is I'm going to teleport it, and then I'm going to do some U gate. And so then the state that comes out here is, of course, U psi. OK, so that's trivial based on teleportation. But the next step is I want to move this U gate back before the poly. OK? So the U gate is here. But now I have to be careful, because I can't just do the same poly as before. If I did that, that's different in general. So what I'm going to do here instead is U, P, U dagger. OK? So, and of course, the way we write them in circuit diagrams is opposite the way they appear in the state. But if you write it in the state, you see this is just, formally it's on this state, it's U followed by UP, U dagger. So the U dagger and the U will cancel. And so it's just UP, what we had before. OK? So this is exactly the same. And this turns out to be a better way to think about what I wrote before as a way of kind of breaking down this U gate. Because now this U is not getting applied to some kind of changeable thing. It's getting applied to a fixed thing, this EPR pair. So what we're doing here is we're taking this state here, which is I tensor U, applied to 0, 0, plus 1, 1. And then the rest of the circuit just consists of this Bell measurement, which is, again, some standard thing, and this gate here, UP, U dagger, which could be a variety of things. But, of course, if U is in the Clifford group, well, I guess it's just one qubit here, then UP, U dagger is in the poly group, right? And so all we've done by doing this is changed from one poly to a different poly, right? So it just looks like teleportation again, but with a different ancilla state here. And we've rearranged the polys relative to the classical measurement results. OK? So but this is still not maybe the most interesting thing. You can actually do some fault-tolerant DAG gates this way. So if you're not doing the 7-qubit code, then you don't have all Clifford group gates available. This will turn out to be a useful way of doing some other Clifford group gates. But I actually want to go even further than that. So let's say that U has some other property, and that for all P in the poly group, UP, U dagger is in the Clifford group. OK? So this means this is a definition that U is in what's called C3. So there's going to be a Clifford hierarchy of gates that satisfy this. We don't really need to worry about the other things in the hierarchy. C1 is the Pauli group. C2 is the Clifford group. C3 is a set of gates that have this property. Okay? And so now let's see what happens if you have this property. Well, suppose you have the ability. Again, I'm thinking unencoded, so it's just this is something that's built into your computer. You have the ability to create whatever states you want, and you have the ability to do Clifford group operations. And that's it. Is this enough to do universal quantum computation? Well, given those abilities, you can do the Bell measurement. And if you find some U with this property, well, you can make this state, because I said you can make whatever states you wanted, right? And if you have some U with this property, then UPU dagger is a Clifford group operation. So you can do that as well. Okay? So the upside is you've at least increased the set of gates you have available, right? Before you could just do the Clifford group gates. Now you can do Clifford group gates plus C3 gates. Okay? And it turns out, and I guess I said this a few weeks ago, that, for instance, well, it's actually the Clifford group plus any gate turns out to be universal. But in particular, Cn plus this pi over 8 phase rotation is a universal set of gates. And so why did I pick this particular gate? Well, R pi over 8 happens to be in C3. So what is that? Well, R pi over 8 x R pi over 8 dagger is e to the minus I pi over 4 R pi over 4x. And R pi over 4 is in the Clifford group. Right? This is the 1I diagonal phase gate. And of course, R pi over 8 is diagonal, so it commutes with Z. Okay? So what this is saying is that if you have the Clifford group gates plus the ability to make whatever state you want, and measurement and classical computation that lets you control the Clifford group gates, then you can do this R pi over 8 gate, and you have a universal set of gates. Now again, this is going to be approximately universal, right? Because it's only a finite set that you're starting with. But then by multiplying them together, you can get arbitrarily close to any unitary that you want. Yeah?
Okay, quick notation question. So C1 over in the bottom left, where U is a member of C1 is the Clifford group, right?
Sorry, C1.
That one is the Clifford group, so that should be C2? Or? No,
okay. Yeah, so, sorry. This is a cursive C, and this is a non-cursive C. So I've been using the cursive letters P, N, and Cn to denote the n-qubit Pauli group and the n-qubit Clifford group.
Okay.
And so this is the 1-qubit Clifford group, according to that notation. And this C3 is the non-cursive version, is the third thing in the Clifford hierarchy.
Okay.
Yeah, sorry. It is a bit confusing.
So curly 1 is equal to non-curly C2.
Yes and no. The thing is that this notation suppresses the number of qubits.
Okay.
And this one is putting in the number of qubits explicitly. Okay. And of course, this definition really will work for n here. This C3 is defined for all n. It's the union over all n. Okay, sorry about that. Okay, so right. So let me just comment that another gate in C3 is the Toffoli gate. So Toffoli gate is really just a classical reversible gate that we're applying to qubits. So it takes ABC to A, B, C plus AB, mod 2, binary arithmetic. Okay, so it's kind of the reversible analog to the AND gate, classically. And so it turns out this Toffoli gate is a universal gate for classical reversible computation. And it's also true, of course, well, yeah, that the Clifford group plus the Toffoli gate is universal. Right. And I guess the other thing is that this construction here, I drew it for 1 qubit gate, but you could also draw it for 2 or 3 qubit gate like the Toffoli gate, right? And then you'd have multiple bell pairs here and multiple bell measurements up here. But otherwise, it's exactly the same. Okay? Is that part clear enough? Yeah.
Minor question. Do we have multiple bell states, or do we use like a cat state?
No, multiple bell states. So remember the same logic. We're working on teleportation. And to do teleportation, you need a maximally entangled state. Maximally entangled state for n qubits with n qubits is n bell pairs, whereas the cat state has only 1 e-bit of entanglement, right? Because by local operations, you can convert it to just 1 EPR pair. Okay? Okay, so what does this have to do with fault tolerance? So fault tolerance, remember, let's think about the 7-qubit code again. So we have the ability to transversally do Clifford group gates. And moreover, it's a CSS code, so we have the ability to do measurements straightforwardly, just transversal measure every qubit. Okay? So if we can create encoded versions of this state, where U is, say, the pi over 8 gate or some other C3 gate, then we can run this circuit on the encoded states. Okay? And that gives us a universal set of gates built out of things that are fault tolerant, except I haven't told you how to make these states yet. Okay? So what we've done is we've kind of rearranged the difficulty of doing these non-Clifford group gates into pieces that we already knew how to do and state preparation. And the advantage of that, I told you again last week in the context of error correction, which is that once we know what state we're trying to make, we can do all sorts of stuff to it. We can try stuff. If it doesn't work, throw it out. We can try again and again. And because we know, we have more tests that we can do. Whereas if we're doing it on the encoded state, well, we don't know exactly what we're supposed to have. Okay? Yeah, so I should say that this state here is called a magic state. And this circuit here is an example of a magic state injection procedure. Okay, so how do we make these states? Oh no. Okay, so one way we can make them, it turns out, is just using some of the tricks we talked about last week, in particular the Shor logical measurement procedure. So how does that work? Well, so this magic state that we're getting, can do it in general. Oh, the eraser's up there. So the magic state we're getting it turns out it's going to be an eigenstate of some Clifford group operators. So what do I mean by that? Well, so 0, 0 plus 1, 1 is a stabilizer state. Its stabilizer is XX ZZ. Okay? And then we apply I tensor U to it. Right? So what does that mean in terms of the stabilizer? Well, if U were a Clifford group gate, you remember we discussed how to do this, right? So we just conjugate X and Z on the second qubit by U. And that's true actually more generally. U doesn't have to be a Clifford group gate. It's just that what we get out instead of this is not going to involve polys. So instead, it's going to be a tensor product. Sorry, it's going to be in the stabilizer. It's going to be fixed by the following operations: X tensor U X U dagger, and Z tensor U Z U dagger. Okay. And so in order to make this state, it's sufficient to project on the eigenstates of these two operators. Right? Just as 0, 0 plus 1, 1 is the plus 1 eigenstate of these two things, this magic state is the eigenstate of these two things. And so if we measure the eigenvalues and we get plus 1, then we're done. For that matter, if we get any eigenvalue, if we get minus 1, well, it's not this state, but we know that if we apply y to the first qubit, we'll change the eigenvalues to plus 1. Okay? So any pair of eigenvalues you can fix to get the plus by doing a poly on the first qubit. So what we have to do is we have to measure these two operators and figure out their eigenvalues. And, well, we know how to do that, right? These are Clifford group things. Because U is in C3. And suppose we're working with a 7-qubit code again, so there's a transversal implementation of these. Well, the Shor measurement procedure that we talked about, that was for polys. We're measuring polys. But really, if you look at it, all it cared about was that there was a transversal implementation, right, of the thing, of the gate that you wanted to measure, of the poly, of the well, the poly certainly is transversal, but of the operator that you want to measure. Okay? So that's one way. Sure. I guess really the measurement. Okay. So that's one way of making these states, and this was the original way that Shor proposed in his paper on fault tolerance. But, you know, as we discussed last week, Shor measurement procedure is a huge pain in the neck. It's not something you really want to have to do. And so nowadays, the more popular way of doing this is called magic state distillation. So it works based on a principle I kind of demonstrated in a very simple case last time for state preparation for the Steen code, which is we're going to create multiple magic states and kind of compare them to each other. Right? So the magic states won't be perfect because we're creating them using a non-fault tolerant circuit. But then when we compare them to each other, we can detect errors and get more reliable magic states. So how does that work? So there's a number of magic state distillation procedures that are known. And some of them, it's kind of mysterious how and why they work. But some of them are more transparent in terms of conceptual structure. And so I'm going to describe one of those. And basically what it's based on is codes that have transversal non-Clifford group gates. So for instance, there's a 15-qubit code. which is, I mean, it's based, so it's a CSS code, so it's based on two classical codes. It's basically a 15-bit Hamming code and punctured Reed-Muller code. So it's kind of a generalization of the 7-qubit code, but it doesn't share this property that you're using the same code twice. You're using different codes, which, remember, have to satisfy this duality condition. I'm not sure if it's very illuminating to write down the stabilizer. But this 15-qubit code has the property that the logical 0 is, so it's a CSS code. It's a superposition of bit strings which all have weight 0 mod 8. And the logical 1 is a superposition of bit strings with weight 7 mod 8. Okay? And so the upshot is that if you apply this r pi over 8 transversally, well, if you apply it to the logical 0 state, the pi over 8, so let's write what's the gate here. So r pi over 8, remember, it looks like this. It's either the minus pi over 8, either the plus pi over 8, I pi over 8 along diagonal. And so if you apply it to something that has weight 0 mod 8, well, so let's say it's weight 0, right? So then you have, okay, so it's easier if you rewrite it this way. So you take out this factor, e to the minus I pi over 8. And then what you have left is e to the I pi over 4 here. And so this global phase here doesn't matter. So if you have something that's 0 mod 8, well, you're applying, for each one, you get e to the I pi over 4. Right? And so if you have 8 of them, that's e to the 2 pi I, 1. And if you have 16, well, you can't because there's 15 things here. But you could have 0 of them, in which case you also get 1. Okay? So if you apply it to the logical 0, you necessarily get 0 again. Nothing happens. All the code words stay the same. All the terms in the superposition stay the same. Whereas if you apply it to the logical 1, well, all the bit strings in the superposition have weight 7 mod 8. And so now you're applying this 7 times, and you have e to the 7 I pi over 4, which is e to the minus I pi over 4. And so what you get is you get the r, well, so on the 1 you get e to the minus I pi over 4, 1. And putting this together, this is the r pi over 8 dagger gate, ignoring this global phase again. Logical. Okay? Okay, so so now let's use this code to make better magic states. So again, I want to think unencoded for a moment. Okay, so forget about the fault tolerance and error correct encode. We just have, again, the ability somehow to do Clifford group gates, and we want to, and we have some unreliable way to make these magic states when U is the R pi over 8 gate. Okay? Okay, now I want to upgrade this into a more reliable way of making these magic states, and therefore being able to do the R pi over 8 gate reliably. Okay? So what do we do? Well, so each one of these magic states lets us do the R pi over 8 gate. But if the state was wrong, the gate will be wrong too. Okay? So what we have certainly is the ability to do this gate here unreliably. Okay? And another thing we can do is we can create this sorry, not the state I want. We can create this encoded Bell state for the 15-qubit code. Why can we do this? Well, this is a code word, a stabilizer code word for a stabilizer code. Right? It's a stabilizer state encoded in a stabilizer code. So we can make it using the Clifford group, which we have available. Okay? So suppose we do that. We make this state, and then we apply the R pi over 8 transversally to it. Well, we're doing this, but the R pi over 8 gates are unreliable. Okay, but let's say that they're at least somewhat reliable. The error rate is not super high. And so suppose they have some probability P of error. Okay? Well, when P is small, probably only one of them will go wrong. Okay? So the probability of 2 bad R pi over 8 gates, which is saying that there were 2 bad states that we made to start with, is order p squared. And the probability of 3 is order p cubed. Okay? But this 15-qubit code, I guess I didn't say this, the 15-qubit code is distance 3. Okay? So if we apply this transversal gate to it, to a code word, and this is a correct code word because the Clifford group is perfect in this assumption. So if we apply this transversal gate and there's 1 or 2 or 3 bad gates, then we'll get 1 or 2 or 3 errors. Okay? And if there's one error, it's a distance 3 code, so we can correct one error on the state. And then we can decode it. So, so this state here, remember, because this r pi over 8 does the transversal r pi over 8 dagger, actually what I want to do, well, yeah, okay. This is a kind of a minor point, but is the logical r pi over 8 dagger applied to 0, 0 plus 1, 1, which is the logical magic state up to this dagger, which is not that important. For the 15-qubit code. So if we correct errors, if there's one error and we correct it, we'll get back this state. And then if we decode, we'll get the magic state. And the probability that we don't get the magic state is the probability that there's 2 or more errors, right? So that's with probability O of p squared. And so you see we've improved things, right? Because if we wanted to just do the r pi over 8 directly on the unencoded state, we could only do that with probability p. But now with the magic state distillation, we're doing it with error probability order p squared. And actually, we can do even better if we want to detect errors. Why is that? Well, if we detect errors, it's a distance 3 code, so we can detect 2 errors. Right? So if there's 2 pi over 8 states that are wrong, then we'll detect those errors, and then we can throw it out and try again. And if we don't detect errors, well, either that means it's correct, or it means there's 3 or more errors. So in that case, we get the correct magic state, except with probability O of p cubed. Of course, the trade-off for this is that we'll be throwing stuff out. So in this case, we just had to try it once. And it was always going to give us something. In this case, we might have to try it multiple times because we might keep detecting errors and say, oh, no good, no good, no good, no good. This one's finally good, right? So that requires more resources to do that. But because it suppresses errors more, it works at a higher error rate. That's kind of your trade-off. Okay? So, so now let me just fill in the dots to make sure it's clear. How do we apply this for fault tolerance? Well, now what we're going to do is we're going to create a state like this, except that it's encoded not just in the 15-qubit code, but each of the physical qubits of this 15-qubit code block are logical qubits of the real error correcting code that we're using for fault tolerance, like the 7-qubit code. Okay? So it's a concatenated code. There's 2 levels of code, which we'll see more of later. So that's like, 105 qubit block code. So it's pretty big. And then when I say decode, I mean decode the 15-qubit code. And then what we get is a magic state that's encoded just in the 7-qubit code. Okay? Now, of course, if it's just in the 7-qubit code, we don't have the ability to do Clifford group gates with perfect fidelity. Sometimes there'll be errors there too. But that just kind of adds another parameter here. It's still the case that so our method of making this state is going to be non-fault tolerant, because what we're going to do is we're going to make the unencoded state not encoded in any code, and then we take each of these 2 qubits and encode them using the 7-qubit code. Okay? And that's what lets us do these R pi over 8s unreliably on the 7-qubit code. And the magic state distillation gives us magic states that are more reliable for the 7-qubit code, assuming the Clifford group error rate is not too high. Okay? And then you can kind of go from there. The point is that because there's multiple gates involved in this non-fault tolerant encoding procedure for the 7-qubit code, the error rate of creating this state is going to be higher than the error rate even for a single Clifford group gate, and certainly then for a transversal Clifford group gate. The logical error rate for a transversal Clifford gate requires 2 physical errors, 2 physical faults. Okay? Does that make sense? Any questions on that? Yeah.
So the only reason we use the 15-qubit code is because it has a nice property of the 0 mod 8 and 7 mod 8?
Yeah, that's right. So it has this transversal implementation of the logical pi over 8.
So other magic state distillation methods are just replacing the 15-qubit code with another code which has some property. But you still encode the bottom layer in some sort of...
Yeah, so, okay. So magic state distillation procedures are basically always discussed in this model that I'm describing up here, where you forget about the bigger context of the fault tolerance. And you say, okay, suppose I just have the ability to do Clifford group gates and to make unreliably certain states. How can I make those states more reliably? And some magic state distillation procedures are based on finding codes that have transversal implementation of some non-Clifford group gate and then working through this same sort of thing. Basically, all of them that I can think of do involve an error-correcting code of some sort. And they kind of roughly follow this model. But like I said, they're based on, some of them we don't really understand how they work. And they're not necessarily based on codes that have a transversal implementation of this non-Clifford group gate. So for instance, there's one that uses the 5-qubit code. And the state it creates is not directly associated with performing a gate by teleportation. It's some other state that you can then convert through some other procedure into a state that you can use as a magic state in a magic state injection procedure. And the reason it works, I mean, you can analyze it, but it's still a little bit mysterious. It has to do with the eigenvalues of this operator and balancing the weights of the code words. And it's, I don't know. I mean, it's not. I couldn't design another procedure like that. That was not just taking these properties and say I need these properties. Let's find the code with these properties. And there's a couple different classes, I would say, of magic state distillation procedures that work in different ways, and it's not really clear what the unifying factors of them are, if any. Okay. This is one where at least you can understand how it works in terms of stuff we've done. Okay. Okay. So let's see. So one thing that is worth saying about magic state distillation procedures, while it's kind of the prevalent way that people talk about creating a universal set of gates, is not the only way. And the problem is that even this magic state distillation procedure can be pretty cumbersome. Because if you have a big quantum error correcting code, as we'll talk about in a little bit, then it's not really enough to suppress errors to order p squared. You want to do it to a much higher order of p, which is fine. You can do this procedure iteratively. So you do magic state. You create these really lousy magic states. Well, not really lousy, but somewhat lousy magic states with order p errors. You distill them to order p squared or order p cubed. And then you put them back in and do this whole distillation procedure again. And that'll give you order p cubed cubed. Right? But again, every time you do that, you're throwing away a lot of them. Okay? And so you can suppress the error rate fairly rapidly, but the actual amount of resources that it takes to do this is quite large. The scaling is fine. Asymptotic scaling is fine. But the actual numbers, when you start to plug them in, turn out to be quite a lot for kind of reasonable sized computations that people are talking about doing. And so people have, in past 5 years or so, people have put a lot of effort into coming up with kind of different sorts of constructions of universal set of gates. And some of them are pretty interesting for various reasons. None, I would say, has taken over as clearly better than this. For one thing, this is fairly general, whereas a lot of these other procedures are for specific codes, whereas this works for pretty much any stabilizer code with the right aspects to it. Certainly for any CSS code, you can do this. Okay, so I do want to say one more thing, which is, so this version that I've shown you of magic state injection is also not the one that people usually do, because there's an optimization which kind of obscures slightly the structure, but is easy to derive, and lets you do it with not a 2-qubit state, but a 1-qubit state. So let me show you how that works. Okay, so again, we're going to kind of modify a circuit, starting with something that's a bit like teleportation. So So there's actually 2 teleportation-like circuits here. So this, if you do this circuit, remember, since we're thinking of these 3 qubits as being next to each other in a quantum computer, we don't really require this EPR pair that's shared between distant locations. All we really want is to be able to have some circuit that just involves Clifford group gates to start with. Okay? So specifically, we're going to use the C0 gate. And so if you have this thing, we have a 0 ancilla, and you do a C0 from your qubit to the 0 ancilla, you measure this in the x basis. And then as this is a 1, you do a z down here. This, like teleportation, always gives you the output psi when the input was psi. Okay? And similarly, this circuit here, where you have a plus ancilla and a controlled not going the other way, and now a z measurement instead. Okay? And again, the point here is that this is a starting point of using Clifford group gates and an ancilla state, and that lets us kind of shift around the U. So let's do it. So for the R pi over 8 gate, what we want to do is we want to work on this circuit for a reason that will be apparent in a moment. So suppose we were to stick in an R pi over 8 here. Okay? At the end here. Well, we can commute it past the x, But again, we have to conjugate. So we get this circuit here. And then the state that comes out is r pi over 8 psi. Okay? So this was just the same thing we did before. And now, this r pi over 8 is diagonal. And this is the control of a controlled knot. So this control doesn't care about the phase of the control bit. It only cares about whether it's 0 or 1. So we can commute this through. Okay? And now we have this circuit. With, instead of the ancilla plus, we have the ancilla r pi over 8 plus. And this thing, of course, is a Clifford group gate, because r pi over 8 is in C3. So again, we have a magic state. A Clifford group circuit, partially controlled by classical computation. And the overall effect is to implement the pi over 8 gate on our state. Okay? So this, of course, is the unencoded version, but you can do all this, say, for the 7-qubit code using transversal Clifford group gates and an encoded magic state. Okay? I guess the other thing worth saying is that this magic state, well, you can, since you can use it to do the pi over 8 gate, you can do the same distillation procedure for it. Except that now, of course, you're not distilling r pi over 8, 0, 0 plus 1, 1. You're distilling r pi over 8 plus. But in fact, you can switch between them as much as you like, because you can use them to do these up. If you have 3 Clifford group operations, these 2 states are equivalent, and they're both equivalent to the r pi over 8 gate. Okay? Any questions on that? Okay. So yeah, so this kind of pretty much brings us to the end of the gate gadgets that I wanted to show you, because now we have a complete set of fault-tolerant operations, right? We have gadgets for error correction and for all the kinds of basic locations that are needed to make an arbitrary circuit, to arbitrary accuracy anyway. I guess I do want to mention one other optimization that people often do. So normally, I've been describing things as when you do an error correction gadget, you'll measure the error synchrome, and you'll deduce what the Pauli error is, and then you'll correct that Pauli error. But the thing is that you don't really need to actually correct the Pauli error. You just need to keep track of it. Okay, so this is called the Pauli frame. And so what do I mean by saying you need to keep track of it? Well, suppose you find that there was an X error on the first qubit, okay? And you don't correct it. So you say, there's an X error on the first qubit, let me just remember that. And then you do transversal Hadamard gate. Well, what's the error now? It's a Z error on the first qubit, right? Unless there's been new errors, of course. So now you do error correction again, and maybe you'll find that it is a z error on the first qubit. Maybe you'll find that, and the thing is that because you knew there was already a z error on the first qubit, you can tolerate even if there's one more error, right? So if you find an error synchrome that corresponds to a z error on a different qubit, you should say, wait, well, hold on. I already knew there was a z error on the first qubit, so I should interpret this not as a z error on this third qubit, but a z error on two different qubits that looks like a z error on the third qubit. Right? That's actually more likely, right? Because that means that there would only be one new error as opposed to the two new errors that you need to get a z error to erase the first qubit z error and give you the third qubit z error. Okay? And so as you go on and you keep doing Clifford group gates, you just need to keep updating what poly you think the error is on. Sorry, what poly you think the error is. Now, all of that becomes more complicated when you run into one of these magic state injection procedures. Okay? And under magic state, I mean, if you did an R⁴/8 gate, well, now you would have to update your poly to a Clifford group gate. And once you start doing that, things become complicated fast. Because then if you do it again, well, now it's something else altogether. Okay? And so you don't want to have to keep track of that. So when you come to a magic state injection procedure, you have to stop and think. And you say, OK, well, what's really going on here? I have some error up here. And then I'm making a measurement. OK? And the measurement, I'm going to get a 0 or 1 outcome, logical. And based on that, I'm going to do some poly. But if I do the wrong thing, then I'm going to do the wrong, well, not poly, I'm going to do some Clifford group gate. Then I'm going to do the wrong Clifford group gate. So I want to make sure, and so that's kind of, you can see this transformation of a poly into a Clifford that way, right? Before I thought there was a poly error. Now, if I followed this through, I think there was a Clifford error. But you don't really have to do that. You can say, actually, at this point, I know. Right? I remember that I've been keeping track of the poly error. And I know that 0 here really means it's a 1, because there was a bit flip error on this qubit. Okay? And so then I do the correct thing here. And then I've kind of reset the poly frame. So that's what we do. We keep track of poly errors. Update them after Clifford group gates. And kind of reset after magic state injection. Just in general, whenever we make a measurement, we convert to classical information. We can absorb, kind of catch up the poly errors. Now it's not a quantum gate that we have to do anymore. It's just classical computation. So we update the thing there. And that is what lets us do the correct Clifford group gate, conditional. Okay? Okay, so yeah, so that's it for fault-tolerant gadget constructions that I'm going to do. Benny will talk about more fault-tolerant gadgets in the context of topological codes. So now what I want to do is kind of bring this all together and show you that actually we're benefiting from doing this fault tolerance. Okay, so in particular, I'd like to show you that if we do a fault-tolerant circuit, that the logical circuit that's happening has a lower error rate than we had with the original circuit. Than if we didn't encode. Okay, so to do that, I need to make some more definitions. Okay, so suppose we have a code that corrects one error, right? Well, if we have a big enough circuit, there will definitely be two faults in it. Well, definitely means with high probability, be two faults in it, even if the error rate is very low. But that's probably okay, right? Because we're doing error correction periodically. And so if those faults are far apart, one will occur, then we do error correction, we fix it before the other one occurs. So what we're really worried about is not having two faults somewhere in the circuit, but having two faults close together, right? At locations such that we don't have a chance to fix the first fault before the second one occurred. So when can that happen? Remember, our circuit, in the simplest version anyway, consists of error correction gadget, some other location gadget, error correction gadget. And so obviously, if you have two faults in the same location gadget, that would be a problem. But it's also a problem if you have a fault in an error correction gadget and then say the gate gadget that occurs right after. Why is that? Well, the one that occurred during the error correction gadget, we might not fix it during that error correction cycle. And so another one has now occurred in the gate gadget before we get a chance to do error correction again. So that's a problem. Similarly, if we get one in gate gadget and then one in the following error correction gadget, that's a problem too. And it's even a problem if we have one in the error correction gadget, the first error correction gadget, and the second error correction gadget, right? Because it could be at the end of the first error correction gadget, at the beginning of the second one, before we've had time to fix the one from before. Okay? So that's kind of the unit of the circuit that we want to look at. We want to look at things of form error correction, gadget, error correction. And if we don't have too many errors in that kind of unit, which is called an extended rectangle, then we should be okay. So let's define it this way. An XREC, so that's extended rectangle. So if we have a gadget for gate or for wait location, then it's the extended rectangle is that gadget plus the EC gadgets before and after. So I should say that if it's a 2-qubit gate gadget involving 2 blocks, then we have 2 error correction steps before and 2 error correction steps after. So a total of 1 gate gadget and 4 error correction steps. If we have a state preparation gadget, then there's no error correction step before because we're starting with nothing and we're getting a state. So it's the EC gadgets after, usually just 1. And if we have a measurement location, then we don't have any EC step after, we just have before. Right. And so then if we have a quantum error correcting code that corrects T errors, we say an XREC is good if it has less than or equal to T faults. And of course, if it's not good, then it's bad. Okay? So this is just codifying what I told you before, that we look at the XREC as the appropriate unit of the circuit, and if it has more than T faults in it, that's an indication that it's not going to work the way we want it to. So we say it's bad. And if it has less than or equal to T, then we should be able to correct the errors. Okay? So the thing about these extended rectangles that makes this a little bit cumbersome is that they overlap with each other. Right? So if you have some circuit that you're preparing zeros, well, okay. So if you prepare some logical zeros, and then you do your error correction gadgets, and then you have some gate gadget, well then you do error correction again, and then measurement. Well, then what do the XRECs look like? Maybe this is a good time to start using color. So this is one XREC, right? This is a preparation XREC, and this is another preparation XREC. And then there's this 2-qubit gate XREC, and then some measurement XRECs in this circuit. Okay? And so this fact that they overlap is going to be a significant complication in just a little bit. Yeah?
We couldn't avoid it by doing 2 error corrections after a preparation and 2 before a measurement?
Not really. So suppose we did that. Suppose we do some gate, and then we do another gate, and then, I don't know, measurement, something like that. Okay, so then we could say, oh, let's have one rectangle that looks like this, and then another rectangle that looks like this. That's what you have in mind, right? Yeah. And so then they wouldn't overlap. But the problem is, suppose that there's a fault right at the end of this one and another fault right at the beginning of this one. That, if this code only corrects one error, that could cause a problem, even though they're in separate rectangles. Okay, so it turns out there is an approach you can do that works this way, but either it's just going to be as complicated in the end, or you have to deal with codes that are kind of correcting more errors. So if you have a code that corrects 2 errors, and you say there can be at most 1 per rectangle, then this will work fine. But that's kind of unpalatable because you're not capturing the full error correction ability of the code. Okay? Okay. So at this point, I need to confess I don't remember what colors I used last time when I was defining these fault-tolerant things rigorously. Does anybody else remember?
I think green was encoded, purple was decoded.
And then the was classical. Yeah.
So green was logical.
Yeah, encoded.
And purple was ideal.
And then red was.
Yeah, there's no red this time, but I'll use orange.
Sure.
I don't really need that. Was the classical. Yeah, okay.
Just for your information, in the video, you don't see any of the colors.
Yeah, okay. I was wondering about that. Anyway, you can figure out from the context. It's just a kind of additional helpful information. Okay, so okay, so yeah, I guess I can put that there. So the next thing I want to define is the notion of correctness. So when I say that things are working correctly, I want somehow to say that the gadget inside the XREC is not getting ruined by the faults, the small number of faults that are occurring. So how do I capture that? Well, it's going to be along the lines of these properties, these, those three-letter properties, various three-letter properties that I defined for fault tolerance. Same kind of idea. So we say that an XREC for a 1-qubit gate gadget is correct if So if we do the extended rectangle and then an ideal decoder, that's equal to, if we just did the initial error correction step and then the ideal decoder followed by the gate. Okay? Does that make sense? Okay, so this error correction, this is like the correctness properties for the gadgets, except that now there's no filters. The error correction, the leading error correction step is taking the place of the filter. And it's serving kind of the same purpose. It's taking whatever junk comes in here and turning it into something manageable. Okay, and then once we've done that, we can say, well, anything that happens after there should be the same between the real version and the ideal version. Okay? And so we say a 2-qubit gate gadget is correct. Not sure if I need to write this out or not, but I will. So now we have the 2-qubit version of this. So for preparation location, sorry, all right. So preparation location, obviously you don't have the leading XREC, the leading EC. So you just prepare, do EC, and then decode, and that should be equal to the ideal preparation. And measurement you can probably figure out, but I'll write it anyway. So now we have the leading EC, but not the trailing one. And so this okay, is equal to so again, this is one where, like the correctness property for measurement, the measurement correctness property, where the ideal decoder only appears on one side. I guess that's true here too, but there's only one side that has something ideal. I mean, the classical bits are ideal, but okay. And of course, if a XREC is not correct, it's incorrect. Okay? So these are much like the things we did before, but are there any questions on them? Okay, so now the upshot of these definitions, so intuitively, the argument I already gave said that if the XREC is good, then it should be correct. And so let's just prove that. Well, I'm not going to prove it for all the different cases. But let's do it for the one block gate gadget, and the other ones are going to be very similar. And actually, this is also very similar to something I did last time, which is showing you how you could put together gate gadgets to make a bigger gadget that was fault tolerant. So the basic idea is we're going to start with the left-hand side here. And we're going to say, OK, so this is a good gadget, a good XREC. So that means that, well, there can be S1 faults here, and S2 faults here, and S3 faults here. But we know that S1 plus S2 plus S3 is less than or equal to T. OK? And this constraint is going to let us invoke all of those fault tolerance properties that we defined before. So, so the first thing we do is, well, all those fault tolerance properties basically needed filters, except for one. One of them allowed us to create filters, and that was the ECRP. Right, the error correction recovery property. So no matter what state you have in, the state that comes out will pass a filter. So we can take this EC here and insert an S1 filter after it. Okay? And then we can look at this thing here and say, oh, well, we have the GPP, the gate propagation property, that says we can propagate this filter forward, right? And so now what do we have? We have this. So this filter, this new filter after, can accumulate new faults, new errors from the faults here. So it could be an S1 plus S2 filter. And then we have this. Okay. And so now, at the end, we have this combination. We have filter, EC gadget, ideal decoder. And so this is the combination that appears in the ECCP, the error correctness property, which says the error correction doesn't do anything to the logical state. It says if you have this combination where this plus this is less than or equal to t, which it is, then you can replace it with this. You have the filter followed by the ideal decoder. Okay? And so now you look and you see something that almost looks like the combination we had with the gate correctness property, right? That had a filter, a gate, and then an ideal decoder. But we do have this extra filter in the way, which is kind of annoying. Luckily, we can get rid of it by applying the GPP in reverse. Remember, we did this last week as well. So the right-hand side of the GPP says that this is equal to the same thing without this filter. Right? The whole point of it is the filter is not doing anything, because we know it has to satisfy that filter. So what do we get? We get, sorry, this is this one. And then we can apply, so we got rid of the filter, and then we can apply the gate correctness property. And so the gate correctness property tells us that we can replace this gate followed by ideal decoder with ideal decoder followed by ideal gate. And then, well, we're almost where we want to get, except that we have this extra filter. And so we get rid of it again using the ECRP. Right? Again, going backwards with the ECRP. So this is equal to and that was what we're trying to show. Okay? And so you can do basically the same argument for all of these cases. Okay? So this is why I wanted to introduce this diagrammatic notation, because it lets you see how the proof works, pushing stuff back and forth through these diagrams. Okay? Any questions on this? Yeah?
The converse of the theorem is not true, right?
That's correct. And in fact, that's a very useful optimization that that people do to proofs to get kind of better values for how things work. So in particular, there will be some combinations of faults. Suppose you have a code that corrects one error, you can have combinations of two faults that don't cause a problem. Right? Like if you have fault on one qubit and then another fault on the same qubit. Right? That'll still just be one error unless they happen to propagate somewhere bad. And your code can correct one error, so that's fine. And other cases, you'll have a fault, in some ancilla, and it just won't be able to propagate into the data in such a way that will cause a problem. So it turns out the number. Well, this will be more evident in the second half, but the bad cases where you have two faults can cause the thing to fail, but it's actually only some fraction of pairs of locations that really cause a problem. And so that means that it's the most naive approach of this would let you would give you some number of how low the error rate has to be, but actually it's less low. Right, and that's exactly because the converse is not true. Any other questions? Okay, so I think we should probably take a break here. Well, okay, so there's one thing to say. So suppose we have a big circuit, a big fault-tolerant circuit. And suppose in this fault-tolerant circuit we have some arrangement of faults such that every xrec is correct. So every xrec is good, right? Then we know that all the xrecs are correct by this theorem. And what that means is that so we have something like this. But of course, probably with many qubits. And what that means is that we can use these various correctness properties in a chain, right? And we can say, oh, well, this is equal to this, where we have an ideal decoder and then the measurement. And then we can say, oh, but now we have, this xrec here, followed by an ideal decoder, so we can push back the ideal decoder even further. And now this xrec, we can push it back, right? And this time, let me not write it. And we can push it back again through the preparation one. And so then at the end, what we're left with is the ideal version of this circuit. Okay? So if all the xrecs in a fault-tolerant circuit are good, the circuit is equivalent to the ideal circuit. So what does it mean equivalent to the ideal circuit? Well, remember that these diagrams are supposed to represent CP maps. So if you have a diagram that starts with state preparation and ends with measurement, well, the measurement gives you classical bits. So it's a CP map that takes no quantum input and outputs some classical bits. Could be a distribution, random distribution. And so what this is saying is that that the fault-tolerant circuit, it outputs some classical bit strings, and after you decode them, you're going to get the same output distribution that you would have with the ideal quantum circuit. In other words, you're getting the right answer to your problem. Okay? So this is the first indication that we're on the right track, that if you happen to have a distribution of faults such that every xrec is good, then you're getting the right answer to your problem. But, of course, it's possible you won't get that. You'll get a situation where most of the xrecs are good, but maybe one or two are bad. So in the second half, I want to talk about what happens then and how you deal with it. Okay, so let's take a 10-minute break, and then we'll come back and do that. So now I want to consider a situation where we have a fault-tolerant circuit, but not all the xrecs are good. Okay, so the good xrecs, we know we can replace them with the corresponding ideal thing. And so the natural thing you'd want to say is, if it's a bad xrec, we'll replace it with the unencoded gate, but with an error on it. Okay? That would make sense. Unfortunately, it's not true. So why isn't it true? So this is a little subtle. The reason is, well, it will be the unencoded gate with an error on it, but the diagram version of that assumes that the error doesn't depend on any of the stuff that disappeared on the left-hand side. Right? So here, let me write down the thing you would imagine saying. So you'd imagine saying that something like this held by analogy. But with an error here, okay? The problem is that this side of the diagram, it doesn't know anything about the faults that happened in this gate gadget and this error correction gadget. By itself, that's not necessarily a problem, okay? Because you could say, well, different faults here correspond to different errors here. That would still be compatible with this picture. You just have to label this error accordingly. But the problem is it's worse than that, because you can have situations where the faults in this gadget will combine with the faults in these gadgets to create different logical errors in such a way that once you do this decoder, see this decoder, this side of the thing does know what the faults in here are, but the decoder erases that information about the faults. And this decoder also knows what the errors are in the incoming state, potentially. I mean, it depends on the exact fault arrangement. But then all that gets erased. And then the error that occurs here might depend on that information. Okay, you can come up with examples where it does. So what we have to do is we have to change the graphical language a little bit into being this decoder extracts the syndrome, it does error correction, but then it throws it away. And so what we want is a decoder that doesn't throw that information away. So this is going to be called a star decoder. And so the star decoder, I'm going to draw this way. It looks like the ideal decoder, but it has another little line coming off the bottom. And this is to keep track of the error syndrome. Okay? And using the star decoder, then I can immediately say what happens to bad XREX. It turns out I don't actually want to do it this way. I'm going to push the star decoder not back to the first XREC, but all the way back to the beginning of the XREC. So what I'm going to say is that this, with the star decoder, is equal to this. Yeah.
So is that error syndrome? That's a classical information, right? Or the star decoder?
Right. No, actually. So this is going to be quantum information. Yeah, and so the reason I need it to be quantum information, and I think I do need it to make this work, is because the possibility, I mean, in what we've been working on, we've just been assuming the faults are Pauli errors. And, but in the more general context, we definitely should not assume that. The faults can be arbitrary things. That means it can be a superposition of different Pauli errors. And I want to include the possibility that there's a superposition of different error syndromes. Because as they accumulate, possibly they could add coherently. And so in order to get everything to work right, at least in the general context, I'm gonna have to assume that this is qubits. That's OK. So you can just kind of imagine doing the same error correction procedure, but you're purifying it. So you're doing everything fully quantumly. All the measurements are replaced by controlled knots to ancilla qubits, stuff like that. And then you just keep all that stuff around. And then most of the time, you just treat it like it's classical. You modify the error syndromes. Well, yeah, OK. So let me explain what this diagram is actually saying. So what this is saying is that this extended rectangle, which presumably is bad, but it is not inherent in this picture, is equivalent to, followed by the star decoder, is equivalent to the star decoder, followed by this gate, but with an error on it that depends on the error synchrome that came out of the star decoder. And then I may have to modify the error synchrome to update it, just like I was talking about updating the polyframe. It's exactly the same way. In this case, we're updating partly for the reasons we updated the polyframe, and partly because there's been new faults that occurred. And we've done some error correction that might have gotten rid of those faults, gotten rid of errors as well. Okay. So all of that can be subsumed into updating the error synchrome. And then I'm just saying that the error that occurred on this decoded qubit depends on what the error synchrome was. Okay. And of course, it can also depend, like I said, on the faults in here. So the exact equivalence between these diagrams will depend on those things. Okay? So great. Now I have something to do with the bad XREX, and I have something to do with the good XREX. But unfortunately, they involve different gadgets. They involve different pictures, right? One is this star decoder. One is the non-star decoder. So that's a bit annoying because it means I can't do this kind of chaining, right? Because if I say, oh, this last one is good, I'll put in a ideal decoder. Oh, but this one is bad, and now I can't push it back anymore. So what I have to do is I have to use star decoders everywhere. And the reason is that good or correct, for that matter, well, OK, actually, it's correct that I want. This is a diagram picture. So if it's correct for regular decoder, that implies that it's correct for star decoder. Why is that? Well, suppose we had this picture here, this diagram equivalence, and then we tried to imagine doing it for star decoders instead. Well, the star decoder here would have to how could it fail for a star decoder, right? It has to be true that, so if you take the star decoder and then you trace out the error synchrome, you get back the decoder, right? So it has to be true that tracing out this error synchrome line doesn't change on either side of the equation what's going on. And so that means that the error synchrome here is unentangled with the decoded state. Okay? Which is exactly saying that if we were to do something like this, that there's no error that's occurring here that's controlled by the error synchrome. Remember, this has to be true for arbitrary inputs. Okay? So what that means is that while this is true for bad XREX, we also have things like this, but with the star decoder for the good XREX. And so we can repeat the argument we made before, but for good XREX. Okay? However, there's still one more problem when we try to do that. So suppose we do this, but then we get a bad XREC. Okay? And we're doing it with the star decoder, so we can continue to push things back. But now what do we have? If we're pushing it back this way, then we've pushed it back all through and gotten rid of this leading EC step. And so now, in this particular diagram, what we'd have is preparation gadget and then star decoder. Whereas the correctness property over here is preparation gadget EC and then decoder. Okay, so we don't have the right thing. So then we also have to deal with is truncated. And they lack the final EC steps. And if you have a 2-qubit thing, you can have something that's truncated just on one block, right? So it might have one of these trailing ECs, but not the other one. Okay? And if you look at it, correctness for a regular XREC should also give you correctness for a truncated one, right? Because this is just saying we'll do error correction, faulty error correction, followed by an ideal decoder, which does ideal error correction, right? So the faulty error correction is not going to help you. It could only hurt you. And for correct thing, it doesn't hurt you. So it's also true that if it's correct for full XRECs, then it's correct for truncated XRECs. Okay, and that's true for regular decoders or for star decoders. Okay, and so then the upshot of that is that given any circuit like this that has a mix of good and bad XRECs, we can push the decoders. We can create decoders at the end, star decoders, and then push them back through. Every time we get a good XREC, we're going to push back to after the EC step. Then every time we get a bad XREC, we're going to push back before the EC step. And the previous one will end up truncated. So let me try to squeeze it on this page. So the upshot is, what we can do is, given a fault path, so this is the set of faulty locations throughout the whole circuit. We have a procedure that we can go through to determine good and bad XRECs and truncation. So I could say, right, well, yeah, OK. So let me mention the other complication with what I've just said. OK, so we looked at it. We had things that we thought were good and things that we thought were bad. But actually, it's more complicated than that, right? Because what is a bad XREC? It's one that has at most T, that has more than T faults in the XREC. What is a bad truncated XREC? It's one that has at most T faults in the truncated version of the XREC, right? Faults that happen in the error correction that we got rid of are irrelevant. So the thing is that whether an XREC is good or bad might depend on whether it's truncated or not, right? Because suppose you have one fault in the early part of the XREC and one fault in the final EC step, right? If T is equal to 1, that's a bad XREC. But if it's truncated, it's now a good XREC. Okay? And the reason I care about this is because I have these overlapping XRECs. And if one EC step happens to have a bunch of faults in it, then it will make both XRECs bad if I don't truncate them. Okay? But that's excessive. I don't want to say that both of these things had to be wrong just because of one concentration of errors, of faults. And so that's why, for the bad one, I wanted to push things back to before this previous XREC. And that's why I had to deal with all this truncation nonsense. Okay, so what we're going to have to do is to determine whether an XREC is good or bad, we have to know whether it's truncated. But to do that, we have to know whether the XREC after it is good or bad. Okay, so we have to go through the whole circuit from the end and kind of work out which ones are good or bad and then which ones are truncated. So we can take the measurement XRECs and determine whether they're good or bad. And then we truncate any XREC before a bad XREC. And then we step back, one time step, and determine if those XRECs are good or bad. And there we should take into account any truncation. And then we simply repeat steps 2 and 3 until we finish the circuit. Yeah. Oh, sorry, that wasn't a question. Are there questions?
It's not guaranteed that we'll end up with a good one, is it?
Well, so this is supposed to be true for any fault path. So some of the XRECs will be good, some will be bad. Could be they're all bad if there's lots and lots of faults. But the point is we're not kind of double counting faults when we do this. That each fault can only contribute to the badness of one XREC. Because if it's if it's in a bad XREC, it's going to be the later. If the one after it is bad, then it's not in the previous XREC. That's what I want to say. Okay. And so when you do this, then you can push back, create the star decoders, push them all the way back through, and so the circuit is then equivalent, this is the fault-tolerant version of the circuit, is equivalent to the unencoded version with good XRECs going to locations without faults, and then bad going to faulty locations. But the catch is, if you follow the diagram through, the actual errors that are occurring on the faulty locations are controlled by this persistent environment. Okay? So the errors are no longer independent errors, if they were to begin with. Does everyone see that? Yeah.
Do you mean like the error that happens afterward always has, or like the incorrect gate always has a line, the same line connected to it?
Yeah. So I mean, if you do what I said and you kind of push back these star decoders through, then you're going to get some line of error syndromes that, you know, every time there's a faulty location, it's the actual error is controlled by this error syndrome line. And the error syndrome line keeps getting updated with these boxes here. But it potentially persists for a long time. Now, actually, it turns out that if you have an error correction step that doesn't have any faults in it, it'll kind of reset the error syndrome, at least locally. But that's we don't need to worry about that in this context. But in general, what I'm saying is that instead of saying that this circuit here is equivalent to this ideal circuit here, it's equivalent to a circuit like this, but with some extra line here that's controlling what the errors are. And that in principle can create correlations between the types of errors at different times. Yeah?
Then also, if it's like a 2-qubit gate, then it's one error line, but it's connected to 2
No. So okay. So if it's a 2-qubit gate, so formally each star decoder is going to give you a separate error line, but this update block will then interact those different error lines. But really, there's no fundamental difference. I mean, we're not saying how big this system is. It could be quite large potentially. And once it's not. It has to be limited by the size of the code, basically. But it doesn't really matter for the formalism if you keep these as separate lines or combine them. I guess that's not true. I mean, you can kind of force some locality into the error by keeping track that they're separate lines.
So I was just wondering, like, if go down later, would the errors be correlated between different lines if there was a previous?
The errors can, in principle, be correlated between different lines because these update procedures, well, first of all, when they appear, they can be correlated. Now, once you've gone through all of this, they just appear kind of as separate things because if you have 1 qubit preparation locations, so they appear as separate uncorrelated lines. But then these updates for a 2-qubit gate will interact them. So it's like gates between the synchron lines. So yes, in principle, that can induce correlations in different locations. But definitely, there's correlations in time. Again, presuming you have for instance, if you have 2 bad XRECs in a row, even with truncation, then you'll definitely have the potential for correlation between them. Okay, so what we're going to have to do, so what I'd like to say is that if you have, now putting in the original error model, if you have a system with independent stochastic errors, and we run a fault-tolerant circuit in there, that's equivalent to a circuit with a lower rate of errors than the original one. Okay, but the problem is that this analysis shows you that those errors won't be independent stochastic errors. So in order to make that kind of statement, I have to generalize the sorts of error models that I'm working with a bit. Okay, but one thing that you notice that doesn't change, which is that the faults in the physical circuit tell us where the faults in the decoded circuit are going to be. Okay, and so in particular, we're not going to get lots and lots of decoded faults unless we had lots and lots of physical faults. And we know that the probability of getting lots and lots of physical faults in a small section of the circuit is not going to be very high. So let's base it on that. So in particular, we're going to define error models which are called local stochastic noise. So it's still going to be stochastic, so we're still going to have some probability. But this probability distribution is going to be a probability distribution over fault paths. Sorry, fault path phi. Okay, so you can think of it just for Pauli errors is the simplest version. And so you say, well, we'll look at the whole circuit, and with some probability, we'll have Pauli errors in this location, in this location, in this location, in this location. Okay? And then with some other probability, we'll have Pauli errors in this location, in this location. and so on and so forth. Okay? So we're just dictating, according to this probability distribution, the sets of locations that have faults. But we don't want to let it be arbitrary. That would be too horrendous. Right? We could have arbitrarily bad correlations then. Instead, we want to say that the probability of getting lots of faulty locations is small. And so in particular, if we have some set S, this should be true for an arbitrary set S, the probability that S is a subset of the fault path is less than or equal to P to the size of S. So S is a set of locations. And the probability that S is a subset of phi, you can rewrite it as the sum over phi such that S is a subset of phi, P phi. So this is the marginal probability of getting some fault path that happens to include S. Okay, so for instance, if S is just a set on the first one particular location, then we're going to include all fault paths. We're going to add up the probabilities of all fault paths that have a fault in that location. It could be the fault path that just has the fault there, or fault path that has one here and one over here, or one here and here, here, and here, and so on. Okay? So basically, what I want to do is I want to say I just care about this set S of locations. And if S is very big, then it's very unlikely that all of those locations have faults. Okay, it's exponentially unlikely. And so we call P the error probability. I mean, it's not exactly, because it's not independent anymore. The possibility, there is the probability of correlations between faults in different locations. That's included in this model. But at some level, we can bound it by errors occurring independently at the different locations and with a probability P per location. Question? No, okay. Are there questions?
You were talking earlier about poly errors in particular. Does it matter what type of an error it is?
No, so here I don't actually want to, I was saying poly errors so you could think about that way. But in fact, not only do we allow non-poly errors, but in order to accommodate the sorts of things we're talking about, we're including errors that are correlated in space and correlated even in time. So, so the errors can be controlled by a shared persistent environment. How do you spell persistent? E. Okay. And so the upshot is that we can apply it to the situations that we've been talking about so far. Okay. So it's worth pointing out that if you actually have an independent model, stochastic error model, it's automatically a local stochastic model, right? Because you can calculate this probability just by looking at this set and say, well, the probability of having a fault on all of those locations is the product of the probabilities on the individual locations, which is P to the S, size of S. So the other thing you can think of about this local stochastic model is that you can think of it as an adversary. So it's kind of a game within adversary. So you flip coins randomly with probability p for each location, and you say, oh, if it comes up heads, it's a biased coin with probability p, it comes up heads, then you say that location is faulty, and if it's tails, you say it's not faulty. And so these are the locations that are faulty, except that they are not necessarily faulty, it's just that they could be faulty. And the adversary gets to take their environment and interact with all the faulty locations in any way that they want. And the adversary is going to try to mess up your fault-tolerant protocol. So they're going to do something that's bad for you. And the idea is that with this local stochastic model, the adversary is not going to get access to very big sets of locations. I mean, over a big circuit, there will still be many, many faulty locations. But for any given set of locations, only a small fraction of them will be faulty, according to this distribution. Yeah?
I just have a question regarding the local part. So, but you can choose a set to be any set of locations, right? So then what does the local imply here?
Yeah, so the local is basically this exponential decay. It's saying that that in this adversarial model that I just described, that the adversary's local access is kind of limited. Okay, and it's limited in a way that's kind of no worse than an independent model. It's just the types of errors that are under the adversary's control.
But it's not local in space. It is too cheap.
No, this is local. So yeah, so there's this unfortunate thing. I mean, it is local in space also, actually, in a sense. So the point is, yeah. So for me, it's much easier to think about it in this adversarial model. And so then you say, well, the types of errors can be correlated in horrible ways, but whether there's faults or not, that's kind of independent. It's not actually independent because the adversary can say, actually, you know, I don't want to put an error in this location. I'm going to turn this fault off. So there could be fewer faults than came up in this random coin flip. And sometimes that's actually advantageous for the adversary, not to put a fault. Right? Like if you had 2 errors in succession on a qubit, the adversary is probably better off not putting a second fault because that might cancel things out, cancel out the error. So it's local in space and in it's kind of some abstract notion of qubits. In that kind of given some region, it's unlikely to affect many qubits, just as if it were an independent thing. It's terminology. You don't have to worry too much about why it's called that. Yeah, I mean, so I guess maybe the thing to say is that there's this other in quantum computing, there's this idea of a k-local Hamiltonian, which is a Hamiltonian whose terms act on k qubits at a time. And that's different than this, but it's kind of a similar notion of locality in that you're saying it's not very many qubits. And again, in that case, there's no geometry there, so those k qubits could be all over the place. In this, I mean, it doesn't matter whether they're near each other or far, so in that sense, it's similar. But mostly it's just saying that it's kind of, there's not many qubits that are affected at once. So that's in the sense in which it's local.
So just to clarify, so then in a sense it's saying the adversary can only pick a small set to play this game on.
No. So this is what I'm saying. So the way to think about this is that the adversary is not picking the set of locations. The set of locations is picked randomly. And then the adversary gets to choose what she wants to do on those locations, which, because they're picked randomly, is going to be a small set with high probability. Okay? Okay. So, okay, so now I want to prove the theorem that says that we're actually improving the error rate. well, actually, mostly I've proven it, but there's just a little bit more I have to do. So this is known as level reduction for reasons that will be more transparent in a minute when I talk about the threshold theorem. So suppose we have a fault-tolerant circuit. And this FT circuit is simulating the unencoded circuit C. And so let's call this C tilde. And C tilde experiences a local stochastic noise model with error probability P. So then C tilde with this noise is equivalent to C with a potentially different local stochastic noise model with error probability P prime. And to make this interesting, I want to be able to say that P prime is less than P. So I'm going to have to put some bound on P prime. So what is that bound going to be? Well, let's look at the arguments that we have so far. So we say with probability P phi, we get some fault path. Okay? And we can look at that fault path, phi, and say, okay, this fault path, we go through this procedure, we'll truncate some, we'll find good and bad XREX, and then the bad XREX will correspond to faults of C. Okay? So that procedure gives us a mapping from fault path phi for C tilde to phi prime for C. Right? And so by adding up all the fault paths that give us phi prime, we have a local stochastic noise model for C. And what's the error probability? Well, what we have to do is we have to look at a set of locations of C and say, okay, these correspond to XREX of C tilde. And what is the probability of having a fault path phi where all those XREX are bad? Right? Well, let's do it just for one XREC to start with. Okay, suppose we have a fault path with one location and one corresponding to one XREC. So what's the probability that that XREC is bad? Well, if the error correcting code corrects T errors, we need to look at T plus 1 locations to have a bad fault path. But it could be any T plus 1 locations to make it bad. Of course, that was the question before. Not all of them will actually cause it to fail correctness. But for this argument, let's not worry about that. So any T plus 1 locations. So how many sets of T plus 1 locations are there? Well, there's A choose T plus 1, where A is the number of locations in an XREC. But actually, I'm going to bound it by the number of locations in the biggest XREC. Okay? And so if I have, and then for each one of those sets of t plus 1, I need all of them to be faulty in order to cause a problem. And so that's a set of t plus 1 locations. The probability of having a fault path that has faults on all of those t plus 1 locations is p to the t plus 1. Okay? So this bound here is correct if you look at single locations of C. That's what the probability of having a fault on a single location of the simulated C. Okay? So, so now let's look at the case where we have multiple locations of C, S locations of C. Well, so that's S different XRECs. And so what's the probability of all of those XRECs being bad? Well, we need t plus 1 faults in the first XREC, and t plus 1 faults in the second XREC, and t plus 1 faults in the third XREC, and so on. Now, of course, there's many different sets of locations in each of these XRECs. How many? Well, each one could have up to a choose t plus 1 different sets of locations. And so we have a choose t plus 1 to the S, if we have S such XRECs. Sorry, let me write this part. So with S faulty locations in C, we have S faulty XRECs. And so how many fault paths can give us that? Or sorry, how many sets of locations in C tilde can give us this set of faulty locations in C? Well, it's at most A choose t plus 1 to the S. Right? And then for each one of these, the probability of those locations being faulty is, well, it's p to the number of locations. And how many locations are there? Well, there's S times t plus 1. Okay? And so the total probability of getting a fault path that causes these specific S locations to be faulty is at most this times this, which you see is this to the power S. Okay, which is exactly what we needed to have this local stochastic error model. Okay? So, so let me point out a couple of things. Oh yeah, okay, go ahead.
Question. So this local stochastic noise model, is it more restrictive or less restrictive than, like, say, the first kind of error model we kind of defined in the?
So that's, yeah. So the independent stochastic noise is a special case of the local stochastic.
So this one encompasses more types of error.
That's right. That's right. Okay, so yeah, so if you think about this, this is why I really needed to do this truncation, because remember, I said I needed to do the truncation because otherwise a bunch of faults in one XREC could cause bunch of faulty locations in one EC step, for instance, would cause 2 bad XRECs. And that would mess up this calculation completely, because then the number of XRECs that, in order to get these S faulty XRECs, I would not necessarily need st plus 1 faults, I could have maybe half that, right? And so again, you could get something, but it would be kind of not taking full advantage of the error correction properties of the code. And of course, if we do have this situation where we have two adjacent XRECs that are supposed to be bad, one of them will be truncated. The first one will be truncated. But that just means it's smaller, right? And so that there's actually fewer things here. And so this causes to do kind of lots of overcounting. We're multiple counting things. But this is just supposed to be an upper bound. And remember, we're overcounting things anyway because we also have sets of locations that, I mean, are bad. They have too many in an XREC, but they don't cause correctness to fail. And so what you could do if you wanted to get a kind of a better bound is to define something that's called malignant sets of locations, which are things that cause correctness to fail for some set of Pauli errors. And then what you do is you count the malignant locations. And that's a little more involved numerically, but you can do it in certain circumstances. You can certainly approximate them. And that gives you kind of improved numbers in this kind of calculation. OK, are there any questions on this? OK, so this theorem tells you that fault tolerance is actually improving the error rate if the error rate is good enough to start with, right? If this is some constant, which depends, remember, this is the size of an XREC, not the size of the big circuit. It's the size of the XREC. So it's just some constant that depends on your protocol. And so like in the case where t equals 1, this is something that's order p squared. So for small enough p, p prime is definitely going to be less than p. And how small that p is going to be depends on how good a fault-tolerant circuit you have, meaning how small you can make your biggest XREC. Or if you're more careful about counting malignant things, whatever those constants get replaced by. So the problem is that going from p to order p squared is not necessarily enough to let you do a really big computation, right? Suppose you had an error rate that's 10 to the minus 3. Then this p squared is 10 to the minus 6, and there's some relatively large constant in front of that. So maybe you have 10 to the minus 4 or something. So before you could do a circuit of size 10 to the 3 gates without having an error. Now you can do a circuit of size 10 to the 4 gates, which is an improvement, but it's not going to let you factor 1,000-bit numbers. Okay, but you might say very reasonably, well, I had this procedure that I could use to take any circuit and turn it into a more robust version of itself with lower error rates. So if I do that once, why not do it again? Okay? And you'd be absolutely right to say that. So doing that will give you a concatenated code and a concatenated fault tolerance procedure. So a concatenated code so you have let's say a stabilizer code, so an N1D code. And this is only really going to work for codes that encode 1 qubit. It becomes much more complicated if you try to encode multiple qubits. And encode each physical qubit with the same code. You don't have to use the same code. You could use a different code, but it's simplest if you use the same code. And then what we get a code with n squared qubits, still one logical qubit. And it turns out the distance is d squared, although that's not going to be terribly important for us. And you can do this L times. So you get L levels of concatenation. And you're going to get an n to the L, 1 d to the L code. And so you can also do this for fault-tolerant protocols. So in other words, you take your circuit, you take each of the locations, you replace it with a gadget and intersperse EC steps. Then you get a new circuit, and you take each of the physical locations of that and encode it again using the same encoding, and so on and so forth. And you do this L times, and now you've blown up the error-correcting code to be one of these concatenated codes. And of course, the whole size of the procedure has grown exponentially with a number of levels as well. But the good side is that every time you do this, you're hopefully reducing the error rate, if the error rate was low enough to start with. And doing this, you get something that's called the threshold theorem. So there exists a threshold error rate such that maybe let's say in a system that undergoes local stochastic noise. With error probability p less than the threshold. Then for all epsilon, all circuits C with T locations, there exists a fault-tolerant encoding of C such that the output probability distribution, let's call the fault-tolerant encoding C tilde, is within statistical distance epsilon of that of C, the ideal version of C. And C tilde uses time, gates, and number of qubits that are greater than C by a polylogarithmic factor. And it's polylog in T over epsilon. So it's a polynomial in the log of the size of the original circuit and 1 over the error rate that you're trying to achieve. Okay? So let me quickly prove this, and then we can discuss it. The proof is pretty straightforward, given what we've done so far. So we're going to prove it using a concatenated fault-tolerant protocol. With L levels. And we're going to figure out what L is in the course of the proof. Okay, so So we have the physical error rate P, and with one level of encoding, here, let's be a little more careful. So with one level of encoding, we're mapping P to P prime, which is less than or equal to A choose T plus 1, P to the T plus 1, where this A is, remember, a parameter of the fault-tolerant protocol, one level of the fault-tolerant protocol, because this is just what's happening under one level. And then when we do this again, we do the same thing. So, so we can do it again and say, so this I'm going to call P sub 1, and this we can call P sub 2 if we do another level of encoding. But let me rewrite this, actually. So it's a little bit easier to see if you call this thing here. Sorry. Let's rewrite it as P sub t times P over P sub t to the T plus 1. So you see that this is equivalent when 1 over P sub t to the t is this. Okay? Sorry, little t. And so this is my formula for P sub t. In other words, okay. Okay. So in particular, like I said, let me be a little more careful. So we have our L levels of concatenation. It has this physical error rate P per physical gate up to the local stochastic noise. And so let's do level reduction to say we can remove one of those levels of concatenation, the lowest level. And now it's a circuit with L minus 1 levels of concatenation and error rate P prime, which is going to be P1, which is this. Okay? And then if I remove a second level of concatenation, and so now it's a thing with L minus 2 levels of concatenation, and error rate P sub 2, which is the same formula but applied to this. So if you take this over P sub t, this first thing cancels out. and we get p sub t times p prime. This is what we're supposed to have for one level, which is equal to p sub t times p over p sub t to the t plus 1 squared. Okay? And then if you do it again, what do you get? Well, so plugging this in, this cancels the p sub t, and we get this t plus 1 squared to the t plus 1. So we get p over p sub t to the t plus 1 cubed. Okay? And you can see that by induction, with L levels, once you've removed all of the levels of concatenation, it's equivalent to the original circuit C with an error rate that's bounded by p sub t times p over p sub t to the t plus 1 to the L. Okay? And so our goal is that p sub L should be less than epsilon over t. Why is that? Well, we have t gates in the original circuit C. And so if we have a p sub L, if we have this is the error rate per gate, then the total error rate of the circuit is going to be at most t times this. And so we want the total error rate of the circuit to be less than epsilon. So this is why we're going to set this bound. And so we should choose L to be, well, plugging, solving, you're going to get yeah, I don't know if you want the whole formula, but I'm going to write it anyway. Okay? Now, most of these things are constant. I mean, the p sub t is a constant. The t plus 1 is a constant. So we only care about the scaling with t and epsilon, really. And so in other words, we're getting something that's O of log t over epsilon. Okay? Okay, so this shows that we can encode with C tilde, it's like the output probability distribution within statistical distance epsilon of C, provided that P is less than P sub T, right? Because if P is not less than P sub T, then this procedure is not going to give us smaller things, it's going to give us bigger things, right? Which translates in here, sorry, this is supposed to be P sub T over P. What translates in here, this thing becomes negative, and then you get a problem. Okay, but I have to say that the resources involved are some polylog t over epsilon factor. So how do I get that? Well, every time I concatenate, I blow up by a constant factor. I blow up the gates, I blow up the time, I blow up the number of qubits by a constant factor. Different constant factors for those different things, but they're still constant factors. So the resource overhead is a multiplicative factor of some constant to the L. Now this looks bad, right? This is an exponential. That seems like a lot of resources. But remember, the error rate is decreasing as a double exponential. So compared to that, a single exponential is like nothing. And so in particular, we have an exponential to log of t over epsilon. And so that's poly log of t over epsilon, which is what I said it should be. Okay? So, 15 minutes. Okay. So discussion. So this threshold theorem is kind of the key enabling result for a fault-tolerant computation. It says that the experimentalists only have to get below this threshold error rate. And after that, the theory of fault tolerance can take over to, in principle, give us arbitrarily good, arbitrarily large circuits. I mean, they have to provide arbitrarily many qubits, of course. But arbitrarily many is only a polylog factor than they would have needed even if they had perfect qubits. Okay? So in the asymptotic regime, this is very good scaling. And it turns out you can actually even improve this further. The problem is that we're not in the asymptotic regime, and we'll never be in the asymptotic regime. We only have ever finite size computers. And if you think about all of the gadgets that I've shown you so far, they involve a lot of stuff. Okay? So the actual constants that appear here, at least using this proof, are pretty large. And probably you wouldn't actually want to use concatenated codes. They're too big and clumsy, at least in this version. So Benny next week is going to tell you about the toric code and surface codes, which are another family of codes that also have a threshold and still have very large constants. And the same asymptotic scaling. They still have large constants, but they're smaller constants, and have an additional advantage that they work well in 2 dimensions. Okay, so theoretically, this is great. In practice, the overhead could still stand to be brought down, even from the best protocols we have today. And so that's an interesting topic for research. So the next thing you might ask is, what actually is this value p sub t? Because if you calculate it and you say, oh, it's 10 to the minus 12, the experimentalists are going to say, forget it, we're never going to do that. So what is the value of p sub t? Okay, so with a concatenated 7-qubit code, so you can go through this argument, and I don't want to actually use this value because that gives a kind of lousy number. So we'll do this malignant set counting, and we'll do some other small optimizations. And even then, what you get is 2.7 times 10 to the minus 5. So that's kind of not completely out of the realm of possibility, but it's still pretty hard. Luckily, fault-tolerant protocols are known that have much higher thresholds. At least we think they have much higher thresholds. So this is a provable threshold. This threshold error rate is, there's a threshold error rate for any given scheme, but what you want is the best one, right? You're going to pick the best scheme. Now, best doesn't necessarily mean the highest threshold error rate, because you care about other stuff like the overhead. But the threshold is kind of a fundamental constant of nature that says, this is the level at which fault tolerance starts working. And so that's for the best possible scheme. So the best one we know, well, we don't know the actual value of the threshold. We have proofs on it, and we have simulations. And the best known scheme simulations suggest p sub t is about 5% with a depolarizing error model. Okay. Now that scheme is also not at all practical. It uses a ridiculous amount of overhead. But as I presume Benny will be telling you, the surface code looks like it has thresholds of a few times 10 to the minus 3, so a little bit less than 1%. And it's kind of vaguely practical, at least to the extent that people are actually thinking that they could build a quantum computer using it. Okay? So questions on this? Okay, so then the very last thing I want to do is to discuss in the threshold theorem, why don't I move that, what the underlying assumptions are and to what extent they're really necessary. So most of these assumptions are kind of embedded in the basic model of fault tolerance that I told you about a few weeks ago. But you have to ask, well, what if the actual physical system I'm working with doesn't satisfy these assumptions? Can I still do fault tolerance? Okay, so let's start with some assumptions about the gates. So we had a particular set of physical gates. Such as the Clifford group and the pi/8 gate. So do we need that assumption? What if we don't have those set of gates? First of all, what if the quantum computer doesn't do those set of gates natively? Well, in that case, we can build those gates or approximations of those gates from whatever the quantum computer can do, right? It's supposed to be a universal quantum computer. So we should be able to put them together into these gates. And, you know, if it takes 3 gates to get a pi/8 gate, then that means the error rate's effectively increased by 3, right? Because any of those 3 gates go bad would cause the pi/8 gate to go bad. Pi/8 gate is not so sensitive. Maybe the Hadamard's C0 would be more of an issue. Okay, but there still will be a threshold, clearly, right? Because once you get these gates, it's just some constant to get them, and then you only have to approximate them to a constant value, and the threshold can correct the rest. Okay. You can also ask what happens if you're given a logical circuit that's not built out of these gates. And then you have to go the other way, because your fault-tolerant protocol gives you logical versions of these gates. And so you have to make the gates that are actually in your algorithm built out of these. And it turns out that doing that introduces another logarithmic overhead, or potentially polylogarithmic, depending on exactly what gate set you're using in the fault-tolerant protocol. So it doesn't change the basic result of the threshold theorem. So this is not a necessary assumption. You can relax it. So another assumption, when I describe these gadgets, I assume that we could do gates between any pairs of qubits. So for instance, you know, the Steen error correction, I said, oh, we're going to have one block of the code and another block of the code, and we're going to do transversal C0s. But suppose you can only do gates between nearest neighbor qubits, right? Well, this whole thing will still work. It's just your gadgets will be bigger, right? Because you'll have to say, oh, I have to move these qubits together and then do the C0s and then move them back to their original locations. And then I have another ancilla, and I have to move that over and do the C0s and move it back. Okay? But each extended rectangle is just a finite number of qubits. So we have to make sure to keep all the ancillas we need nearby the data block, and then we can do this. So again, this is not necessary. You still have a threshold with nearest neighbor gates.
But it has to remain transversal.
Yeah, so, right. So in 2 dimensions, yeah. The problem is I'm basically out of time, so I can't discuss this at length. But yeah, you have to be a little careful about how you do this. And in 1 dimension, it can be pretty awkward. And you probably take a significant hit in threshold to do that. In 2 dimensions, well, in 2 dimensions, as I said, probably the best thing to do is to use the toric code, at least the best that we know of so far. So another thing that we need to do that won't necessarily be true of all implementations is to produce 0 states on demand. So why do we need to do this? Well, when we do error correction, we want to bring in some ancillas, and we interact them with the data and then use that to figure out what the errors are. But the problem is if we had to only create 0 states at the very beginning of the computation, those ancillas would have been sitting around, and we have a very long computation. Those ancillas, by the end, will have been sitting around for a very long time, and they'll have accumulated errors on them. So we kind of do need a way to produce 0 states on demand during the computation. Now, that can be relaxed a little bit, but basically, you need some way of cooling things, right? It doesn't have to be perfectly cooled, but if you can cool to some kind of state reliably during the computation, that's a way of resetting the ancillas that you need and lets you create them when you need them. So another thing, you can say measurements during the computation. Do we need that? Or is it enough just to have measurements at the end? And relatedly, reliable classical computation. What if we don't have that? Or it's not fast relative to our quantum computer? So again, this is not necessary. And the reason for that is you can take all of these classical circuits and implement them using qubits. Okay? You can do any classical circuit using qubits. The problem is that the qubits, by assumption, are not reliable. They can have errors. So when you do this, you have to implement them with a fault-tolerant classical circuit, this repetition code. Okay? And probably this will again hurt your threshold, but you will still have a threshold. So another thing that we assumed is we have a big quantum computer. We want to do error correction everywhere at once. And the reason we wanted to do that is because of storage errors, right? If we only did error correction on this block and then waited on the other ones, and then we did error correction on this block and error correction on this block and error correction on this block, storage errors are still occurring on the ones that we left behind. Okay? And by the time we're down here and have finished the whole computer, these ones, they've decohered. It's way too late. Error correction can only correct things if the error rate is low enough. So some level of parallelism is necessary. It doesn't have to be on all pairs of qubits at once, but it has to be on a constant fraction so that you can do error correction at constant intervals on every qubit in the computer. Okay. Then we have to talk about assumptions about the errors. Okay, we assumed that each location has the same error rate in the proof. Whereas you could have different types of locations have different error rates, or even different instances of the same gate have different error rates over the course of the computation. And clearly this is not necessary, it just makes it simpler. And then we had this local stochastic error model. And so there's two aspects of that. There's the local part and the stochastic part. The local part is saying that the error rate is decaying exponentially with a number of qubits that have errors. And we need something like that. Okay? Because, well, suppose we have an error model where every qubit in the computer goes wrong with some small probability. Well, we're never going to be able to correct from that, right? Like a meteor comes down and destroys our computer, killing everything. Or there's a power outage, maybe more likely. Right? That's a massive correlated error. It can happen, of course, to a classical computer just as likely as a quantum computer. The real world does have such things, unless you're really distributing your computer very far and wide. But the probability is low enough that we can ignore them most of the time. So this is necessary. So another thing was the model that we talked about was mostly just sending qubits to qubits, right? But we could have error models where the qubits leak out of the computational space. Like if you have an ion trap and the ion escapes from the trap, right? If you don't do something to replace it, clearly this is going to be a problem. But, you can replace it. That's not a big deal. And in fact, leakage errors are, at least in principle, easier to deal with than general errors because you can see, oh, this ion is missing. There must be an error there. Whatever I'm replacing it is not going to be right. Okay? So that becomes a located error, right? An erasure error, which is easier to correct. So this is not necessary, but you do need to do something to handle it. And actually, these gates by teleportation are very convenient, right? Because they move you to a different block of the code. So if you had leakage on the first block, the new block doesn't have correlated leakage, right? It's new qubits. So that's a nice way to get rid of leakage without really having to think about too much what's going on. So another thing, this is actually something that you might hope to improve. So this local stochastic noise model, I said you should think about as an adversarial model, which is an adversary that's looking where the faults are and picking the worst possible one. You might say, well, that's unrealistic. Of course, it's unrealistic. Really, we have some noise model that maybe we hope to understand reasonably well. So we have some idea, this kind of error is more likely than this kind of error. And so you might say, can we design a fault-tolerant protocol that takes advantage of that? And the answer is no, or at least we don't know how to. So currently, we don't know how to gain any kind of advantage by using your knowledge of more detailed knowledge of the error model. And finally, there's this point about stochastic errors. So if it's not stochastic errors, what are the other possibilities? So it could be coherent errors, like over rotations of qubits. That's a very reasonable and realistic type of error. It could be non-Markovian error models, where you're interacting with a persistent environment. I allowed that in the type of error, but I didn't allow it in the probability of error, right? So in the real system, it's not going to necessarily be a stochastic non-Markovian thing. But it turns out that we can prove that there is still a threshold, at least for wide variety. And so there's some non-Markovian models where we don't have a proof. My expectation is that it is still true for kind of any non-Markovian model with some notion of locality like this. But it's difficult to prove that. Nevertheless, we do have actually for quite a very general non-Markovian model, and that's covered in the book. Now, one big open question is to what extent these types of errors can hurt your threshold. If you just kind of follow the math, it seems like they should hurt it a lot, basically going to the square, because basically intuitively what's happening is you're setting a bound on the amplitude of error rather than the probability of error, right? Which means that the probability of error, instead of being 10 to the minus 3, is 10 to the minus 6, roughly. Okay, so that's much worse. It's not at all clear that that actually happens. That requires all the errors to kind of conspire to build up in the worst possible way. And there are some techniques you can use to make it even less likely that that would happen. But it's still kind of an open question if in the kind of most general situation where you have non-Markovian errors interacting with your computer, whether it actually does happen in a realistic system. OK, so thanks. I went a little bit over, but this is my last lecture. Like I said, Benny will be taking over. Remember to turn in your problem sets. I think John has some to deliver to you, graded problem sets. And I have solution sets as well. Yeah?
I have a question regarding the bounded correlation, the necessary component.
Yeah.
The necessary component stems from the exponential decay, right?
Yeah, that's right.
In order for the fault tolerance theorem.
That's right.
I mean, as long as you have some sort of exponential decay component there, as you scale up.
You will have a threshold. Okay. So for instance, if there's a component of 2-qubit correlated errors, but many qubit correlated errors still decay exponentially, you'll have a threshold. Probably it'll be worse. That hasn't really been heavily studied. It might not be too much worse, depending on the nature of the 2-qubit errors. Yeah, there's a couple of other issues, which is that you want the marginal single-qubit error rate to be kind of constant with the size of the computer, which if you have 2-qubit errors with a constant rate, no matter how far apart they are, then as the computer gets bigger, the total probability of an error on this qubit will diverge, right? Because you have kind of crosstalk with arbitrarily many things. But that's not a very realistic situation. So. Any other questions? OK, so then